So today we're going to cover the famous Gersavaria. What is Gersavaria and how do we use it for graphs of motion? Well, stay tuned because that's today's lesson. Gersavaria. Before we start, I'd like to show you a very simple tool. Here is a graph of distance versus time. On the left, we can see that it shows the motion of a car speeding up forwards. On the right, we see the motion of a car slowing down forwards. Now, come on. How many movies have we watched about people going fast? We like it when people go fast. It makes us smile. So therefore, if you can put a smiley face on a distance time graph, that is showing an acceleration or speeding up forwards. Let's put it in English. And of course, the same is true on the other side. Well, if you're slowing down, that's not a good thing, then we have a sad face. And that would show a car slowing down forwards. So I hope that will help you remember whether it's speeding up or slowing down just from the shape. So when do we use what? We've got displacement, we've got acceleration, we've got velocity. Sometimes we work out the area, sometimes we work out the gradient. When do we use what? Well, this is the tool that I use, and it's called Gersavaria. Now, you might say that's a very unusual looking diagram. How on earth am I possibly going to remember it? Because what I want you to do is every time you get a graph of motion in an exam, I want you to quickly scribble down Gersavaria. I want you to draw this. But if you draw it wrong, it's going to be 100% useless. So it's very important that you draw it properly. So here's how I remember Gersavaria. The story goes back to when my little boys were toddlers, and they used to love dragging this crate of Lego or Duplo around the house. And it was fun to watch them spill it out and exert their authority over their toys. And the first few times it was fun and it was cute. But you know what? When you get home from work one day and that's what you're facing as you walk in the door, it's not exactly cute anymore. So on this particular occasion, I said to my lad boy, please clean up. I'm going to go and change in my bedroom. When I came back, would you believe it? It was worse.
Did you make all this mess? Hey? Did you make all this mess? Let's see. First it started here in the crate. And then it got spread to the entire house. Oh my word. Let's see, does it go down the passage?
So what does any normal parent do? Well, they change the tone of their voice when the person is not doing what they wanted. In fact, it might come across as a bit of a growl. So we're going to remember that. Grrr. I'm growling because I'm angry. All right, I'm so very angry. So we're going to have grrr, and remember, he's smaller than me. So my hand is pointing down at the time. So we're going to remember the grrr with an arrow pointing down. This is very important. If you get the arrow wrong, this is 100% useless. So grrr and the arrow pointing down. Now the speech starts. Now the parent starts telling off the child. And you'll say something along the lines of, I am so very angry. But I'm growling, remember? I'm so very angry. And I'm upset. Now I want you to remember the word upset has the word up in it. And that's going to help you remember the up arrow. So we're growling and pointing down. We're so very angry. And we're upset pointing up for the way you have left this area. All right, so we're growling, we're pointing down, so very angry and upset about the state of the area. And there you have it, Gersavaria. So how do we use this now? Why have I bothered to teach you this? Well, let's have a look. If you write this down in the exam and they give you a displacement time graph, so the S, the V, and the A will represent a displacement time graph, a velocity time graph, and an acceleration time graph. Whichever graph they give you, you will circle the one that you've got, and you will see, right, if I want to go down, down means go through the gradient. So if you calculate the gradient of a displacement time graph, you will get the velocity of the vehicle. You see, the arrow said go down and V is below S. Let's see, what if I give you a velocity time graph? Well, if I work out the gradient of the velocity graph, which means go down, I'm going to end up working out the acceleration of the vehicle. So the gradient of a VT graph gives you acceleration. And if you work out the gradient of an acceleration graph, well, that gives you nothing. Nothing useful anyway. Let's see if it works backwards. If I give you an acceleration time graph and we work out the area under the graph, well, we see that that gives us the velocity that the object will achieve by the end of that acceleration phase. If I give you a velocity time graph and you work out the area underneath it, well, then that will give you the distance the vehicle will travel during that time period, or the displacement of the object. And of course, if I give you a displacement time graph and you work out the area under that graph, it gives me nothing, or at least nothing useful anyway. So let's go see how it works. Here is a velocity time graph, and we're asked to work out the gradient of the graph for the first 75 seconds. Well, it's a VT graph, right? And the gradient will give me the acceleration of the vehicle. If we go work out change of y over change of x, that will be 15 over 75. I will get an answer of 0.2. But let's look at the units. That's meters per second. So that's meter per second squared. And as we know, that is the unit for acceleration. So the gradient of a VT graph gives me acceleration. Let's look at the same graph, but now from an area perspective. Remember, if we look at the area under a VT graph, according to the up arrow, that should give me the distance traveled by the object. So what is the area under the complete graph? Well, we've got the triangle part, which is green, and we've got the rectangle part, which is a bluish color. And if we work out the area of those two segments, we get this answer, 937.5. But again, look at the units. We're taking meters per second and we're multiplying it by another second. So the seconds cancel out, leaving me with meters. So therefore, the area under a velocity time graph gives me the displacement of the car. So let me give you a strange scenario. Here's a distance time graph with a curve in it. We already said that the area under this graph gives me nothing useful. But what about the gradient? According to Gersavaria, the gradient of this graph should give me velocity. But it's a curve. How on earth am I going to get a gradient? Well, we know this is accelerating, so we know this vehicle is speeding up. But let's go and have a look. There are actually two gradients in the diagram. The first gradient is what we call a secant, right? A line that goes from the starting point to the end point. And if we slide that down, it becomes a tangent to the curve. So we have a secant, which cuts the circle at 2 points, and we've got the tangent to the curve, which touches it at 1 point. And we can see here it is touching at the 5-second mark. If we go and work out the gradient of the secant, we see that we're going to get a velocity, but we're going to get an average velocity, because essentially you're taking the total distance, dividing it by the total time. That will give you an average velocity of 11 meters per second.
It's going to be slower than that earlier on and faster than that later on.
So how do we work out the instantaneous velocity at a particular time? Well, if we take the gradient of the tangent, you see that will give me the instantaneous velocity. So you take the gradient of the tangent, and in this case, it's 88 divided by 8, and we also get 11 meters per second. So it just so happens that this particular vehicle had the same instantaneous velocity at 5 seconds than its average velocity over the whole 10-second journey. But let's go and do a steeper gradient. So here we have later in the journey, let's say the tangent is at 8 seconds. So at the 8-second mark, this vehicle was traveling with an instantaneous velocity of 16.9. You see, it's faster. And if we go earlier in the journey, let's say a tangent at 4 seconds, then we get a instantaneous velocity of 9.2, which is slower than the 11. So the gradient still gives me the velocity of the vehicle. Gersavaria works. For extension, some of you might be asking, well, how would we work out the area under a curved graph? And they might give this as an extension question in a GCSE paper, or they will possibly give you something like this in an A-level paper. So what you would do is you would take the motion that you've been provided with and break it up into either tiny little slithers of rectangles, and you would work out the area of each rectangle and then just add them up. Or, as you can see on the graph on the right, they divided the journey up into squares and worked out the sum of all the squares. So they're never going to give you an exact value, but the finer and thinner you make those strips, the more accurate it'll be, but it's very often taken to be an estimate. And now you know how to use Gersavaria.